Alright guys, today's goal, the learner will understand exponential and logistic modeling. So we're going to be looking at constant percentage, rate, and exponential functions, exponential growth and decay models, using regression to model population, and other logistic models. So let's take a look at the first example. Alright, so what is a constant percentage rate? Suppose that the population is changing at a constant percentage rate R, where R is the percentage rate of change expressed in decimal form. Then the population follows the pattern shows. P0 or P sub 0, that's the initial population. So the initial amount is when the time is 0. Okay? As it grows, you have the initial amount plus the initial amount times the rate. Where you factor it out, you get the initial amount, 1 plus R. Okay? If you do 2, it's still, so you still have P sub 1 times 1 plus R, so that's P naught, 1 plus R squared. So our equation ends up being the population based on time equals the initial amount times 1 plus the rate to the number of years passed or months or whatever the problem's dealing with. Okay? So there's the definition of population. Now, if it's decreasing, that rate will be a negative, so it will decrease. If it's increasing, that rate will be a positive. Okay. If a population, P, is changing at a constant percentage rate R each year, then P of T equals P naught times 1 plus R to the T, where P naught is the initial population, R is expressed as a decimal, and T is time in years. Tell whether the population model P of T equals 786,543 times 1.021 to the T is exponential growth function or exponential decay function, and find the constant percent rate of growth. Okay, so I know P naught is 786,543. And I know 1 plus R equaled 1.021. So if I subtract that 1, I get R is positive 0.021. So you know now it's growth because this is greater than 0. And it says it wants the constant percent rate of growth. This is the decimal, so multiply it by 100, you get 2.1% growth. Okay, so let's take a look at some more. It says determine the exponential function with initial value 10, increasing at a rate of 5% per year. Okay, so we know it's growth, so we have P of T equals, what's the initial? 10, 1 plus 0.05 to the T. So that's 10 times 1.05 to the T. Okay? If that would have said decreasing, you would have done 1 minus that. Okay, let's take a look at some more. Suppose a culture of 200 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. Okay, so if I'm doing that, I have P of T equals 200 to the initial amount. Well, doubling means you have the initial 100% plus another 100% to the T. So I would get 350,000 equals 200 times 2 to the T. So now we need to divide both sides by 200. So you get 175 equals 2 to the T. So now you need to do natural log of both sides, because remember, that means we can bring it down, so you'd have natural log of 175 equals t times the natural log of 2. divide by the natural log of 2. So you get t equals natural log of 175 divided by natural log of 2, approximately 7.45. So if we look at that, let's go back up. It's approximately 7.45 hours. Well, so it's approximately 7 hours, 27 minutes. Okay? Let's take a look at a little more. Okay, so we have some data here. It says use 1900 to 2000 data and exponential regression to predict the U.S. population for 2003. Okay, so remember what I did was I said let x equal 0 for 1900. So in my calculator in list 1 I entered 0, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Then entered all these. I left out 2003 because it says to use 1900 to 2000. I did the stack calc and exponential regression is what I chose. This is what it gave me. So our equation is y equals 80.55 times 1.01289 to the t. So what would I need to do for 2003? It would be 80.055 1.01289 to the 103rd. Just calculate that. That would be your answer. Here's the biggest thing. You have to remember that this population is in millions. Okay? All right, let's take a look at some more. Maximum sustainable population. Exponential growth is unrestricted, but population growth often is not. For many populations, the growth begins exponentially, but eventually slows and approaches a limit. That growth is called the maximum sustainable population. So yes, initially things grow and grow and grow and grow, but at some point they start leveling off, okay? So let's take a look at an example here. Okay, a high school has 1,500 students. 5 students start a rumor, which spreads logistically so that S of t, so the students, equals 1,500 divided by 1 plus 29e to the negative 0.9t. Models that the number of students who have heard a rumor by the end of t days, where t sub 0 is the day the rumor begins to spread. So A, how many students have heard the rumor at the end of day 0? Okay, well, what would we do? S of 0 equals 1,500, 1 plus 29, e to the 0. Okay, so calculate that. So about 50 students. Now it says, how long does it take for 1,000 students to hear a rumor? So that means we got to do this. 1,000 equals 1,500, 1 plus 29 e to the negative 0.9t. Okay? So I'm going to multiply by the denominator, divide by the 1,000. So I'm going to get 1 plus 29 e to the negative 0.9t equals 1.5. Okay. I'm going to subtract the 1. 29e to the negative 0.9t equals 0.5. Divide by 29. So e to the negative 0.9t equals 0.5 divided by 29. I want as exact answer as I can get. So now I need to do natural log of both sides. So I have that. Bring the negative 0.9 t down. Now, why did I get rid of this? Because natural log of e is 1. I'm still just trying to keep everything exact, so I haven't entered anything into calculator. Now I divide by negative 0.9. Let's see what we get. You get t equals approximately 4.5 days, so 4.5 days. Okay? See you guys tomorrow.